All right, we are looking at worksheet A67a. There are notes on perfect squares and difference of squares. So we are still factoring, and then we're going to go on to use our factoring to help us solve things. So without a calculator, it says write the two square roots for each number. So what times itself equals 4? 2 times 2. So 2 squared is 4. What else times itself equals 4? What else times itself equals 4?
-2.
-2. So the square roots of 4 would be 2 or -2. And the reason is because 2 squared equals 4, and so does -2 squared equals 4. All right, so the square root of 36, the principal root we always say is what? 6, but it's also -6. The square root of 81 we know is 9, but we also know it could be -9. And the square root of 144 is 12, but it could also be -12. Now I cannot take the square root of a negative number, but something times itself, a negative times a negative, will give me back that positive. All right, so just as a number can be squared, 4 squared is 16, a binomial can be squared. The result of squaring a binomial is a trinomial. Now a trinomial has how many terms? 3. This is called a perfect square binomial. Okay, so the idea is this is a perfect square because it's something times itself, but it's a binomial. So I cannot distribute a power over addition and subtraction, but what I can do is write it out twice and FOIL it. So our answers are going to look like this when we factor. How do I expand this? I'd write w plus 6 times itself. So the most common mistake at all levels is that people would write this as w squared plus 36. They think that they can distribute it and get w squared plus 36. That is wrong. You cannot distribute power over addition and subtraction. So you write it out twice. No, there's going to be a middle. And we FOIL this, right? First times first is w squared. Then we do our outside. The inside is a positive 6w. And last is positive 36. So I just use my FOIL acronym to help organize that. And whenever you're done with this, you would add like terms, and we get w squared plus 12w plus 36. So the idea of this is, if I gave you this problem, w squared plus 12w plus 36, and we factored it, the factors of 36 would add up to 12. And so it's the same idea we've been doing, but we wanted to show this relationship. So if you try to just square the first and last term, you would get the first and last, but you would never get that outer and inner to make that 12w. So you can't just distribute. You need to write this times itself. If it was a power 3, you'd write it out 3 times. All right, take a second and FOIL that, please, and add like terms.
Can I text my coach real quick?
Sure. So first is x squared. The outside is negative 5x. The inside is negative 5x. And last, negative times negative is going to be a positive 25. So you should have those 4 pieces, and then you're going to add like terms. So we get x squared minus 10x plus 25. Okay. So when you see this, this looks like all the trinomials we've been doing. Okay. And you guys are actually pretty good at factoring these now if you've been trying them. And the reason I say that is because these are those easier ones where the one's out front and the factors of 36 add up to 12. The factors of 25, 5 and 5 add up to 10. And if I need a negative 10, negative 5 and negative 5. So do you see that this is the same idea? If I gave you this, you come back and factor it. All right, so what's the pattern? How do I pick out a perfect square trinomial? The first term is a perfect square. Isn't x times x a perfect square? The first term here, w squared, is a perfect square. So the first term is a perfect square, and the last term, 36, is 6 times 6, or 5 times 5. So the first and last terms are perfect squares. Now, I don't expect you to sort of memorize this, but some of you would catch it. The middle term, that minus 10x, is double the product of the roots. If you think about it, you had a product of the root was x and negative 5, negative 5x. And if you double it, you get negative 10x. That happens because the outside was negative 5x and the inside was negative 5x. There's two of them. Okay, so do you have this jotted down? First term is a perfect square, last term is a perfect square, and the middle is double the product of the roots. So here we go. We're going to determine whether these are perfect square trinomials or not. Okay, so it actually doesn't ask us to factor it. We're just going to do it anyway. All right, is the first term a perfect square? N times n. Is the last term a perfect square? 5 times 5. Is the middle a product of those roots? The square root of n squared is n. What's the square root of 25? 5. So if you double 5n, you get what? 10n.
It's the exact same thing. Wow.
It is. So it's asking, is this a perfect square trinomial? Yes, and here's why. N times n, that first term, and the last term, I would do 5 times 5. Now, I need a positive 25. So not only is the last term a perfect square, it has to be positive. All right, how am I going to get this positive 10? Plus and plus. Do you see the outside's 5n and a second 5n? There's double the product. All right, is this one a perfect square? If I look at it quickly, k times k and 7 times 7, does it work?
Yep.
Nope.
Yep.
Because the middle would have to be a what? 14k. So it is not a perfect square. If we try this, k plus 7, k plus 7, where am I getting this from? First term, last term, 7 times 7. The outside is 7k and the inside is 7k. What's that add up to? 14k. So not a perfect square trinomial, but it looks like it because the first and last were squared. Okay, look at C. What's a big difference here compared to all the ones we just looked at?
It's got a number.
It has a leading coefficient. So if you think about this, what do you know about the number 9?
It goes into 3 times.
It's a perfect square, 3 times 3, right? So the first term might not just be a variable. So let's break this down and see if it works. I'm going to write this as 3x and 3x. Now, there's other options. 3 and 3, my other options are 9 and 1. But if I'm looking to see if it's a perfect square, I'm going to try the perfect square factors. All right, what gives me 4? 2 and 2 or 1 and 4. So I'm trying the double digits. Plus 2 and plus 2. Okay, first works, right? 3x is 9x squared. Last, 2 times 2 is 4. Did I get the right outer and inner to make this 12x work?
No.
Well, 3x times 2 is 6x.
Oh,
Yeah, and another 6x. So this is yes, it is a perfect square trinomial.
Yes.
All right, you try the next one and see if it works out.
Nope.
So the big answer is yes or no, and then we were testing them. Is 16 a perfect square?
Yes.
Is x squared a perfect square? So first term is a perfect square. Is 1 a perfect square?
No.
1 times 1?
Okay, I guess.
Okay. Is the middle double the product of the roots? Well, let's check it out.
No.
4x, I don't know why you guys are such non-believers. 4x times 4x is 16x squared. Now, what's going to give me 1? 1 times 1. Do I want plus plus or minus minus?
Plus, plus. Minus.
I want minus minus.
Oh,
So here's the deal, guys. My last number always has to be positive. Negative 4 is not a perfect square because it's not something times itself. That's negative 2 times 2. But this works. Look, you get a negative 4x and a negative 4x, which is negative 8x. So yes, this is a perfect square binomial if you factor it. All right, now we didn't do all this, but how would my final answer look for all of these? Something times itself is written as a quantity squared. So something times itself you'd write as 3x plus 2 squared. So here are these perfect square trinomials that make a squared binomial. We would write this as 4x minus 1 times itself, so squared, and k plus 7 quantity squared. Okay, so those are your perfect squares. Now go ahead, it says to factor these, and it says don't forget GCF. So first, is there a GCF here? No. Okay, A is 1, so the factors of 64 will add up to 16. Now, if you're looking at this and it's all mixed up, take the pass. N times n is your n squared. And what multiplies to get 64? And that's what I'm going to try first. A positive 8 times a positive 8. Does it work? N times n is n squared. 8 times 8 is 64. Now what about that outer and inner? Yeah, that's 8n and another 8n. See how it's double the root? 8n times 2 is 16. Final answer. To get full credit, you have to show this final answer as a quantity squared. You're pointing out and saying, hey, I caught this. It's a perfect square. All right, now letter B. Does it have a GCF? No. No, because the y out here doesn't. Okay. But y squared is y times y. 100 is a perfect square. What times itself gives me 100? Are there other options to multiply to get 10? Absolutely, lots of options, but I'm trying the 10 and 10 first because I always try the perfect square first. Okay, what kind of signs do we want? 2 negatives. You always have to have the same sign. A perfect square always has to have that plus sign here. Okay, negative 10 times negative 10 is 100. My outside, negative 10y. My inside, negative 10y. So this is the same thing we've been doing. The difference is I don't have to work as hard if they're a perfect square. Y minus 10 quantity squared. Now, is every problem you're going to get that looks like a perfect square actually going to be one? No, we saw this on the front. It started and it ended with a perfect square, but the middle didn't work out, so you're still testing it. Okay, C. What do you see?
36. I see.
Okay, well, there's a couple things here. It starts and it ends with a perfect square, so some people are going to jump right in and factor it.
4 is the GCF.
There's a GCF, so I'm actually always going to do that. So the GCF comes out first, and you're left with 9x squared plus 6x, and don't forget plus what? 1. It's still a perfect square, guys. What multiplies times itself to get me 9x squared? A 3x and 3x. What multiplies by itself to get me 1?
1.
All right, now, what kind of signs do we want? They have to be the same size.
Positive.
Yeah, a positive and a positive. All right, so if we're checking it, that's 3x and that's 3x. Does it add up to my 6x? Yeah. All right, now final answer. Don't lose your 4. And it was this thing, 3x plus 1 quantity squared. Okay, now, real quick, because I think some of you jumped in. If you would have jumped in and you weren't wrong, 36 is a perfect square. You could have said 6x times 6x. Do you agree that that's 36?
Yeah.
And a positive 2 and a positive 2, that multiplies to 4. And the outside is 12x, and what's the inside? So it factored, right? 12 and 12 is your 24. What's wrong with leaving this answer? 2 things. 1, you'd have to write as a quantity squared, but do you see you didn't factor it completely? You need to factor 2 out of here and a 2 out of here, and guess what you'd have out front? A 4. So it is important to do your GCF first because most people forget it later. All right, I'll give you a second. You try D. Yeah, I know. It's always someone else.
It was Candace.
It's always the quiet ones.
Look at her face.
She's despicable.
Candace. Hey, Michael. I got $20 because I need to activate in my store. Okay. That's funny. I just went off for what it said.
All right, so we have this 4x squared we broke down to 2x times 2x. To get the last term 1 times 1, what kind of signs do we want?
Negative.
We want two negatives. A negative times a negative is going to give me that positive 1. The outside is a negative 2x, and the inside is a negative 2x. So no GCF here. Final answer, the quantity 2x minus 1 squared. So these look no different than the factoring we've been doing. I mean, this could mix right in with your problems. The difference is we're always starting to try and say, hey, can we use the perfect square to get this? Okay, so in these examples, both binomials were either sums or differences. So we had a plus plus, we had a minus minus, and now we're talking about a different pattern. I'm talking about this math and you're listening. So a different pattern develops in the product of two binomials that are similar, but one binomial is a sum and the other is difference. As in, you will have it and it will look like this, 1 plus and 1 minus. Okay, so this is called a difference of two squares. So let's talk about this. We've actually already seen this before. Whenever you look at this, if I FOIL this, the first times first, that's y squared. The outside is a negative 9y, and the inside is a positive 9y. And last, 9 times negative 9 is negative 81. So what happens with these two middle terms? They cancel out, and I'm left with y squared minus 81. Now, if you think about this, remember our whole ax squared plus bx plus c? If I rewrote this, I know there's a y squared there, it would be something like ax squared plus 0x minus 81. This is what a difference of squares really is. Your first term and last term exist, and your middle term is 0. That's why you need one positive and one negative of the same thing, so the middles cancel out. So a polynomial such as this, or a polynomial such as, we'll go with a minus b times a plus b, which really is a squared minus b squared, is called a difference of two squares. So if I have a squared minus b squared, a times a is a squared, negative b times b is negative b squared. The outer is positive ab, the inner is negative ab, which cancels out to 0. All right, so if you can recognize the polynomial as a difference of two perfect squares, so it says difference of two squares, has to be a minus sign. We can work backwards. Not everything that looks like this is factorable. All right, so first example. What's different about all of these problems compared to the ones we did? We're missing the middle. This would be the same as saying k squared plus 0k minus 9. So this is your first and this is your last. What's your middle? Your middle is 0. So take the square root of k squared. K times k. What gives me negative 9? One positive, one negative. I'm going to go with the positive 3 and a negative 3. So this should actually be really quick factoring as long as you recognize it. K times k is k squared. There's other factors in negative 9, but the 3 times negative 3 gives me negative 9. And the outside, they're the opposites of each other. Negative 3k, and the inside is positive 3k, which is 0k.
So is that stubbing little k plus 3k minus 3?
That is my final answer, and you cannot write it as a quantity squared because it's 1 plus 1 minus.
That's what I figured out.
So if you look, again, I only have two terms. I'm missing the middle. So my first times first is y times y. What gives me negative 144? I need a number times itself. 12. Now how do I get it to be a negative?
1 positive, 1 negative.
That's it, guys. The order of your signs does not matter as long as we have these two combinations. There's your y squared. There's your negative 12y. There's your positive 12y. That cancels out to 0. And 12 times negative 12, negative 144. Okay, same deal. No GCF. You want to look for that.
11.
What you need to catch is m times m and 11 times 11. Now, I need a negative 121. That's what's different. M times m, one positive and one negative. There's the negative 11m that's going to cancel with the positive. So always double check yourself. Okay, look at D and E. Those are different, aren't they? What's different is you have a number up front. So first, is there a GCF? 16 doesn't go into 81. 8, nope. 4, 2. Okay, so no GCF. But what's important about the number 16 and important about the number 81? They're both perfect squares, yeah.
You didn't tell us to do it.
Oh, you should be one step ahead of me. All right, what gives me that 16x squared? We said it was a perfect square, so I want to use 4x and?
4x.
Okay, now I could use 8 and 2, and I could use 1 and 16, but we're going with the square root. What gives me a negative 81?
1 positive, 1 negative 9.
1 positive 9, 1 negative 9. Now, when we go to do this, 4x times 4x is 16x squared. The outside is a negative 36x. Remember, that changes because the 4. And the inside is a positive 36x, which adds up to what? 0x. And last, there's your negative 81. All right, look at E. Now, the first thing I catch is there's only 2 terms. That's what makes these so different than these guys up here. 64 is a perfect square, and so is 100. But can you tell me something else? Did you look for a GCF?
Yeah.
Well, what is it?
8.
No, just 4. 2, but 4 is the GCF. So 4 goes into 64 16 times. And how many times does 4 go into 100?
5.
I was going to go with 25. Okay, so now that I have the GCF, it stays out. What times itself gives me that 16x squared? 4x and 4x. What gives me my negative 25? What multiplies by 7? 1, 5 that's negative and 1 that's positive. Okay, I'm leaving the 4 out there. 4x times 4x, there's your 16x squared. 20x and negative 20x is 0x. And there is my negative 25. Okay, now let's just say you didn't take out the GCF in this problem. You would have factored this as 8x plus 10 and 8x minus 10. It works. 8x times 8x is 64x squared. 10 times negative 10 is negative 100. Negative 80x and positive 80x. What's the problem with this? It's not factored completely. You could have taken a 2 from here and a 2 from here, which would have given you your what? 4. So to get full credit, you have to take out the GCF. You okay? But these are my final answers. All right, how about F? What is it? Okay, so you need to put an X here and an X here. Okay, factors of positive 4. Remember, they have to add up to 0. Yeah, not going to work for me. Okay, so here's the deal. X times X is X squared. 2 times 2 is 4. The problem is you just got me a 2X and a 2X, which adds up to 4X. Now, to correct it, I heard make 1 positive, 1 negative. The good news is you've now fixed the issue. Negative 2X and 2X cancels out, but am I still getting a positive 4? If I tried 2 negatives, when I end up adding up to negative 4X? Okay, guys, this is prime or not factorable. And here's the key. Remember how we called this a difference of 2 squares? It has to be a minus sign. If you look, when you have 2 terms, it has to be a difference. There are no factors of 4 that add up to 0. Remember, this is x squared plus 0x plus 4. I have to have the positive and the negative, so when I do the outer and the inner, they cancel out to 0. So pay attention that it has to be a difference of squares.